Electromotive force is probably the worst named quantity in the history of physics. Okay, we're going to talk about electromotive force. And it's not a force. And electromotive, I don't know what that means. Something's moving, sounds like electric car or something. I don't know. Here's why they named it this. Okay, this is a very interesting story. Somebody had the bright idea of taking two different metals, and I think it was zinc and copper. And then they put like wet paper towels in between them, and then like soak the paper towels in orange juice or some other kind of electrolyte or something, and they made the first electric battery. Yeah, I don't know. These people needed, I'm glad they did it, but I can't even imagine. Okay, so, yeah. So, and then what they did, so they came up with the first electric batteries. So what they would do is they would take one metal, and they would put some gunky stuff, between them, some electrolyte, some kind of conducting material, okay? And then they would put a different metal. It's a metal sandwich. And then they would put another layer of gunk. And then they would put the first metal. And then another layer of gunk. And then they would do that. Then they would hook up a wire like this. And they found that they could get a little spark. Not much. But what they did, and they were sick people. They would take a frog and they would cut the frog in half.
You really got to take that. Oh my god. Oh god. Oh, that's really good.
Okay. So here's the head of the frog down here. It's been cut. All right. Okay. What?
The arms are gone.
Okay. Now, I hope they at least ate them after they were done with these experiments. But what they did was they took this wire and they touched it to the frog. And guess what happened? The legs kicked. Which is very hard to draw. But they kicked. And they said, oh, there must be some force involved here that's forcing the legs to kick. And they called it the electromotive force because it was forcing the legs to kick. Now, we know today that this was sending a very tiny electric current that ran through the muscles that basically shocked a dead frog. And now it won't it's got to be a freshly dead frog though, okay? So if you're going to try this at home.
He's not fully dead, he's just mostly dead.
He's just mostly dead. Okay. So they called it the electromotive force. But here's what it allowed them to do. And they named it that, so that's what we call it. Yes?
When they made this metal sandwich, why was it their next impulse to get dead frogs?
That's the question. I don't know. These people were geniuses, but they were kind of weird. All right. Which just tells you that weird people have a place in our society.
It's called robotics.
Yes, it's called robotics team. All right. Now, but this was a profound discovery. This was a very profound discovery because for the first time, you had a steady current was possible. See, before they came up with this, and I believe this was in the very early 1800s that they made these discoveries. before that, like in the 1700s, when you had Benjamin Franklin and those people doing electrical experiments, everything they would build up a static electric charge and you would get a spark. And so you would have a very brief current, and it would be a little electric, spark. And it would not, it would be very brief. And it would be at an extremely high voltage. But once we did this, we now had steady currents. We could have a current, a march of electrons through metal wires that were constant with time. Now, the electrochemistry of this guy here is outside the scope of this class. Okay? And actually, I think you study electrochemistry in AP Chemistry.
Yeah.
Okay.
Too bad.
So, I'm not going to cover that. I'm not going to discuss why metals with different, they have different work functions and all that kind of thing. They cling to their valence electrons with different amounts of clinginess. And so by taking advantage of that difference, you can actually create, and a chemical reaction takes place in here, and it actually drives electrons through the wire. Okay, so now what electromotive force actually is really the change in voltage that you get from a battery. And so electromotive force is a very old-fashioned name. But electromotive force is often abbreviated EMF, which we abbreviate further by just calling it E, kind of this cursive E.
Okay, so it is the cursive E, and it wasn't just getting fancy.
Yeah,
Okay.
it is a cursive E. Now, it's nice to call it a cursive E because it distinguishes it from an electric field, okay, or mechanical energy. But what a cursive E represents is the voltage of a battery of cells, or just one cell, when no current is flowing through it. Thank you. Yes, all right. Can I turn in your take-home test right here? Okay, now, when no current is flowing through the battery. Now, some of you on the robotics team, you may have noticed that when you're measuring the voltage of the battery, when there's no current flowing through it, it's a little bit higher, isn't it, than when it's under load?
I mean, like when the battery dies after 5 minutes.
What's that?
Like when the battery dies after 5 minutes, it's totally awesome.
Well, yeah, but I mean, why is that? Why would the battery deliver a less voltage to the circuit when there's current flowing through it than when there isn't current flowing through it? And that's what we're going to talk about here. You see, let's take a look at a battery. Let's just draw the symbol for a battery. Okay, so here's my circuit, and I'm going to talk about the EMF of the circuit, the electromotive force. Sometimes it's and well, if let's say the switch is open here, there's no current flowing through it. Okay, and this is I'm going to call this R sub L. This is my load resistor. Well, what this represents is, what am I trying to deliver current to so that something will happen, wheels will turn, lights will flash, whatever, or heat will just be given off. But you close this switch, now you get a march of charge through the circuit, and here's our current. Now, really, in reality, oops, I didn't draw that very well, did I? There's this. Really, what's happening here is electrons are marching in this direction through my DC circuit here, direct current. They're moving this way, but because current is defined to be the flow of positive charge, we say that the current is in this direction. So in our imaginations, let's imagine positive charge carriers marching through these wires. And so they come in here, they jump down, they deliver all their energy. But then they have to come back here, then they have to go through the battery. They have to physically go through this battery. And when they do, they run into stuff. I mean, there's atoms and there's chemical reactions and things that they got to go through. And they're going to run into stuff. And so in other words, the battery itself, the material that the battery is made out of, itself has its own resistance. And I'm going to draw a little bitty resistor in there, and I'm going to say, here's my battery. Here's my D-cell battery. Okay? Okay? So in here are all these electrochemicals that deliver a voltage, that boost the voltage when you go from one end to the other, from the negative end to the positive end. But if current is flowing through it, you're going to heat up the battery. Several years ago, a colleague of mine, his students were doing an experiment with batteries, and what they did was they lined up a whole bunch of batteries in series like this, like a whole bunch of them. Like, I think they were C batteries. I mean, they had like 10 of them. And then they took a bare wire and they did this. They just hooked it up with a wire, a big thick wire. Now what's the resistance of a wire? Not much is the answer. So there's very little load resistance here. So what happens? Well, V equals IR, solve for I. I equals V over R. There's hardly any resistance. So the current was very high. It's called a short circuit, right? You get a burst of current through your circuit. Well, what happens here is that the batteries themselves are the resistors in this circuit. The wires do get hot, so the wires themselves have a little bit of resistance. But so anyway, these kids come running into my room from his class and they said, Mr. Lake, check it out. You got to come over here. And so I went over and looked, and they had this thing, and there was smoke coming off the batteries. Isn't this cool? And they're all staring at it with their face about 3 inches away. That's bad, okay? Because batteries will explode if they get too hot. Now, it's not an explosion like a hand grenade, you know. You're not going to lose, a face. You're not going to lose your face. But you know what? It could spit some very caustic chemicals into your eyes. It could.
Glasses.
They weren't wearing any safety glasses, no.
Mayor's mistake.
All right?
Why were they doing this in this kind of class?
Because it was cool. You hook all these up. It was a physics class. Now, I immediately grabbed them and pulled them away from it, and I said, no, you can't do that. But anyway, the point is that the batteries themselves have some resistance. So what you do is when you measure the voltage of a battery while current is going through it, you're actually measuring the voltage that it's delivering to the load, okay, which is going to be a little bit less. Okay, remember last time we talked about Ohm's law. We said the voltage drop across a resistor equals I times R. That is, we get a voltage drop across a resistor when current is flowing through it. And so, but if you think about the battery like this, here's the EMF of the battery. this right here, the resistance that is in the battery itself, it's called the internal resistance. It's usually very low compared to the rest of the circuit. Of course, not in the one where the batteries were smoking, but usually, and we usually use little r for internal resistance. Here's my load resistor here. And so I want you to think about voltage man. Here's voltage man. And here's this cape. Okay. Now, measures voltage here. Let's just go on a voltage walk around this circuit. Starts at 0. And actually what I'm going to do is I'm going to draw this circuit a little funny. I'm going to start here, and then I'm going to have the battery like this, and I'm going to give it some width, okay? And then I'm going to show the internal resistance right there, and then I'm going to show the load resistance right here. And I'm going to march from here over to here, and then you can kind of think of a little thing that runs back like that. And you start over again. And what I'm going to do is I'm going to graph as I walk. I'm going to graph what my voltage is here. So this is going to be voltage. And you know what? You know what I'll do? Is I'll draw it below. Okay. So let's say I'm right here. Voltage man starts here and starts walking up the circuit. So we're walking up the circuit. Our voltage is 0. Until we get here. And then as we move through the battery, you can kind of think of boom, like this. I gain voltage. But this is the voltage that the battery delivers to the circuit if there's no current flowing through it. This is my EMF of the battery. So we gain voltage as we move through the battery. Now if the switch was open and there was no current, if there's no current, there's no voltage drop across the resistor. But look, right here. Here's my load my internal resistance. I'm going to drop a little bit of voltage. I'm going to drop a little bit. And this is my battery heating up a little bit. My battery's going to get a little bit hot. So energy is leaving the circuit right there. There it goes. Then we go through a wire. Now we're going to assume here that the voltage drops that are due to the lengths of wire in our circuit are insignificant. Okay, we get to do that in physics. If you're a real circuit designer, quite often you have to take those voltage drops due to resistance in wires into account. But we're not going to. And then we reach our load. And and so when we get here, boom, all the energy that was left after we finished moving through the battery, all the energy that and then we're back down to 0 volts. And then we go back to the beginning and start over again. So you think of these charge carriers moving through here. They have 0 energy per unit charge. Boom, you go through the EMF of the battery, but because there's current, you're going to lose a little bit. And then over here, then you're going to lose the rest of the voltage. Now what's the voltage drop here? Well, the voltage drop here is going to be the current times the internal resistance of the circuit, of the battery. And over here is IR sub L. This is the voltage drop due to the load. The thing we're delivering the energy to that we want. Now, these two voltage drops, what do they have to be equal to? The voltage gain of the EMF. You're going in a circle here. Voltage man always completes his circuit. He always goes in a complete circuit. Yes?
Okay, so going back to the, when you're talking about the robot battery, higher than the actual voltage you get when it's on the robot. That's EMF,
Yes.
right? Okay, so you're measuring it after or before you get to little r.
Mm-hmm.
And it's little r that you're not taking into account, which is why
Right.
it's
But
more.
but see, when you're not running any current through the battery, if your current is 0 times your internal resistance is 0. There is no voltage drop. There's no voltage drop to measure because there's no current.
Okay.
And so all you're doing is measuring the voltage gain due to the EMF of your battery.
So the second flat line after before you get or after little r, between little r, that one, yeah, you see run it. No. That one. That one's the one that you're actually getting off the battery.
Well, you remember when you use a voltmeter or whatever, you're only measuring a voltage gain or a drop. You put your black lead here, you put your red lead here, it'll read negative whatever volts, and because it's a voltage drop. Okay, we're going to talk about voltmeters and ammeters in here in a little bit, but you always have to put your voltmeter across something, right? What if you had a voltmeter and you put your black lead here and your red lead here? What voltage are you going to measure? 0. Because there's no voltage difference. Does that make sense?
Yeah.
Okay. Now, so what we can say here is something quite profound. We can say that the voltage gain due to this, and then you have minus IR minus IR sub L equals 0. In other words, these represent voltage drops. IR and IR sub L, they represent voltage. So the voltage gain, plus these voltage drops, or so you subtract them, equals 0. Of course it has to be. You're back where you started. There can't be any voltage difference between if you finish where you start, there can't be any voltage drop. And there can't be, I gain voltage, I lose voltage, and I'm back where I started. So there's no change. Is that clear for everybody? Okay. I think that is enough for this one.